Welcome back. This is third lecture on class 11th chemistry, chapter 2, structure of atom. In the previous lecture, we read about Rutherford's model of atom and saw its various drawbacks. So the next model which came into place after Rutherford's model was the Bohr's model of atom. In this lecture, we shall see the important developments which played a major role in the formulation of Bohr's model of atom. So how did Bohr's model of atom come into place? We shall read about all about that. So two important developments played a major role in the formation of Bohr's model of atom. First, dual character of electromagnetic radiation, and second, experimental results regarding atomic spectra. So electromagnetic radiation have dual character. They have both wave nature as well as particle nature. Let's study more about this in detail. First, wave nature of electromagnetic radiations. So what are electromagnetic radiations? In the early 1870s, James Maxwell suggested that when electrically charged particle moves under acceleration, then electrical and magnetic fields are produced. These fields are transmitted in the form of electromagnetic radiations or electromagnetic waves. So let's discuss the characteristics of electromagnetic radiations. Electric and magnetic fields produced by oscillating charged particles are perpendicular to each other. So in electromagnetic waves or electromagnetic radiations, the electric and magnetic fields are perpendicular to each other as well as perpendicular to the direction of wave propagation. So all three of them are mutually perpendicular, as you can see in the diagram. Also, electromagnetic radiations do not require any medium to propagate. So unlike sound waves, they don't require any medium to propagate and they can even travel in vacuum. And through electromagnetic radiations only, the heat from the sun, the light from the sun reaches the earth. And there are many types of electromagnetic radiations which together constitute the electromagnetic spectrum. So let's study about this electromagnetic spectrum. So in electromagnetic spectrum, there are different regions for different types of electromagnetic rays like X-rays, gamma rays, UV rays, IR rays, microwaves and radio waves. So you can see that there are different regions of different colors for all of them. And the small portion in the frequency of 10 raised to power 15 Hz is of visible light, which can be seen to us. And all the other rays cannot be seen by us. So only the visible light, that is VIBGYOR, violet, indigo, blue, green, yellow, orange and red, only that small portion can be seen by us and all the other rays are invisible. Now let's discuss properties of electromagnetic waves. First, wavelength. So the distance between two adjacent crests or two adjacent troughs is called wavelength. So as we know that electromagnetic waves can be represented as crests and troughs, so the distance between two adjacent crests or troughs is called wavelength. Its symbol is lambda and its unit is meter. So you can see that that symbol is of lambda. Second, frequency. Its symbol is nu. The number of oscillations per unit time is called frequency and its unit is hertz, represented by Hz. Third, velocity. Its formula is lambda into frequency, that is wavelength into frequency. For an electromagnetic waves, velocity is equals to the speed of light, that is velocity is equals to 3 into 10 raised to power 8 meter per second, that is the speed of light. And the symbol of velocity is c. So there is an important relation between wavelength, frequency and velocity, that is velocity is equals to lambda into frequency, that is wavelength into frequency. Fourth, wave number. The number of wavelengths per unit time is called wave number. So wave number is equals to 1 upon wavelength. So let's discuss few limitations of wave nature of electromagnetic radiations. Wave nature of electromagnetic radiations could not explain following phenomena. First, black body phenomena. Second, photoelectric effect. And third, line spectra of atoms. So all these three things it could not explain. These can only be explained by particle nature of electromagnetic radiations. So this proves that apart from wave nature, electromagnetic radiations also depict particle nature. Now let's study about all these three phenomena in detail. First, black body radiation. So what is black body? Black body is an ideal object which emits and absorbs radiations of all frequencies uniformly. So a normal object would emit and absorb radiations of different frequencies at different rate. But black body will emit and absorb the radiations of different frequencies also at the same rate. Thus, it is an ideal object. In order to explain the black body radiation, Max Planck in 1900 put forward his quantum theory known as Planck's quantum theory. In this theory, Planck suggested that atom could absorb or emit energy only in discrete quantities of small packets and not in a continuous manner. So in this way, he challenged Maxwell's theory of EM radiations and said that the energy transfer is not continuous. He gave the name quantum to the smallest quantity of energy which can be emitted or absorbed. Energy of a quantum of radiation is proportional to frequency. That is, energy is proportional to frequency. So if we remove the sign of proportionality and put a constant in that, so it will become that E is equals to h nu. That is, energy is equals to h into frequency. Now what is h? H is a constant and it is known as Planck's constant. Its value is 6.626 into 10 raised to power minus 34 joule second. Now let's discuss about photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons were ejected when certain metals were exposed to a beam of light. So when some certain metals were exposed to a beam of light, then electrons were ejected, as you can see in this diagram. This phenomena is called photoelectric effect. Now, there were few observations when this experiment was conducted. First, no electrons are ejected from a metal if the incident light has frequency of less than the minimum frequency value called the threshold frequency. So if the frequency of the light wave is lesser than the threshold frequency, the minimum frequency, then the electrons will not be ejected. Second, the number of photoelectrons ejected is directly proportional to the intensity of brightness of the incident light. Third, the kinetic energy of the ejected electrons is directly proportional to the frequency of the incident light. So all these three observations were observed when photoelectric effect was conducted. All these observations could not be explained on the basis of laws of classical physics. So the laws of classical physics could not explain all these results. But in 1905, Albert Einstein was able to explain photoelectric effect using Planck's quantum theory. So from our discussion till now, we have concluded that electromagnetic radiations show dual nature. Sometimes they show wave nature and sometimes they show particle nature. So this was all for today. In the next lecture, we shall discuss that using all these observations, how Niels Bohr came to an atomic model of atom.